speaker of this session will be Yuri'san from Zhongshin University. NTHU. Sangong University. Really?
Zhongshin.
University. So I was right. so let's welcome her.
Thank you. I'm Yuri'san from National Zhongshin University, and my collaborators and the supervisors are here. And I'm going to talk about the follow-up observation of fast radio burst using FIRST. Okay, let me go to the introduction. So FRB, or first radio burst, is a radio transient with a duration of milliseconds. And it was discovered in 2007, so it's relatively 70 years ago, so it's relatively newly discovered astrophysical phenomena. And what's special about FRB is that they have large delay in signal arrival time, depending on the frequency due to the free electron in space. And thanks to this, we can tell that almost most FRBs are extragalactic origin, but we still don't know the exact origin of FRB, and that makes FRB study very interesting because we have plenty room to study about it. And there are 800 of FRBs discovered so far, and the burst rate of all sky burst rate is 1 burst in 1 second. Then FRBs are one of the most energetic events in the universe, so the energy release per burst could reach up to 10 to 40 org. Then there are apparently two types of FRBs. One is one-off FRB, and the other is repeating FRB. If we observe one burst from the single source, we call it one-off FRB. And if you observe more than one burst from the same source, we call it repeating FRB. And remember that some portion of repeating FRB is hiding inside one of FRB population, because think about the one source that bursted 2 times, then if the radio telescope is not operating either when either one burst happen, we have no choice but we classify this FRB as a single, is one of FRB, not a repeat, while it's actually repeating FRB. Okay, then what FRB research more complicated about is that there are many irregularities. For example, these 2 FRBs, they are known as repeat many more than the usual repeating FRBs, and they are called highly active repeating FRBs. And those repeating FRBs can be burst up to 100 times within an hour. And there are more than 50 FRB theories proposed to explain this phenomenon, but there is no single theory that can explain all the FRB features. So I hope by now we have the same consensus that in order to understand FRB better, the first step to understand it, the important step to understand FRB is classify if whether or not the FRB is one-off or repeating. Because if it's truly one-off FRB, we can associate with this one-off FRB with the theory that happen only one time in a star lifetime, like a neutron star merger. And if it's repeating FRB, we can associate this repeating FRB with the physical mechanics that happen multiple times, such as star quake or a flare from the highly magnetized neutron star. And in order to find repeating FRB that is hiding inside the one of FRB population, there are many observations were conducted. But finding the repeating FRB is very difficult. For example, these 2 previous observations, they spend up to 100 hours to find the repeating FRB, but without succeeding in the finding repeating birth. So the classification of repeating and one-way FRB is very time-consuming, and you could waste many observation hours if it's not repeating FRB. And that's the reason why our research group proposed two methods to classify one-off FRB and the repeating FRB from the single epoch observation. And one approach is empirical approach with Hashimoto 2020 focused on the physical feature of repeaters that is fainter in luminosity and longer in duration than compared to one-off FRBs. And the other one is a machine learning method. Chen 2022 proposed a method to classify these two types using the UMAP, which is the machine learning model good at visualizing the multidimensional data. And so let me explain the light figure. This figure, each small dot represents the observed FRBs. There are 500 of them, and the black and the blue color represents the one-off FRBs, and the red color represents the repeating FRBs. And this is representing the relationship between 11 physical parameters of FRBs, which is FRBs that can obtain from the observation, such as frequency, and also the signal duration and the flux. And as we can see, there are several clusters in this two-dimensional figure, and if FRBs are inside the same cluster, which means they have the similar physical properties. So the blue one-off repeaters, which is inside the same cluster with the repeating FRBs, they are likely repeat in the future. Okay, so using these two methods, we selected the repeating FRB candidates. Then, in order to test our method, we proposed the observation using FIRST, which is the largest single-dish radio telescope in the world, and the PI is my supervisor. Then we selected the 36 FRB candidates, then which sample size is 5 times more than the previous similar research. And the observation was conducted in 2021 to 2022. Then we observed those FRB candidates 10 minutes each, and this 10 minutes is optimized time so that we can maximize the chance of detecting repeating FRBs within allocated time, which is 12 hours. Then frequency is about 1 to 1.5 gigahertz, and we use the Presto software, which is a common software to find the pulse-like signal in radio frequency. Then the reason why you wanted to use the FIRST is because FIRST has the better sensitivity than other radio telescopes, and it is known that the subsequent bursts from repeating FRB, the more fainter signal can be appear than the stronger signal, and that is why FIRST is best suited to find a subsequent burst from repeating FRBs. Okay, then let's go to the result. So interestingly, we find very faint signals, such as these two examples showing here, and their signal to noise ratio is about 4, which is our detection threshold. So we don't report it as a detection in this time. So from our non-detection result, we set the upper limit on the FRB's repeating rate. Then this gray triangle marker, they show the previous research, result from previous research. And this red triangle circle is our research from this time. Then we set the 10 one order magnitude stronger upper limit than the previous research in general. And this means that the periodicity of repeating FRB is much larger than the previously assumed. Then finally, I want to mention that one of our targets that has been selected by the machine learning method was actually turned into a repeater, which is confirmed by the other research group. So, and also, we have another set of data that's waiting to be processed. So our research they continued, and please stay focused on our research. Okay, thank you, and here is the summary.
One automatic model is a big change. So what does that imply in terms of all the property of physics of FRB? What's the implication of your result?
Well, we believe that this implies that the repeating rate of FRBs is much longer than expected.
How about the number of next star and well, for example, the mass function of next star or the probability of neutron star merging. How does that related to this repeating rate?
Well, I'm not sure how it's related, but yeah, I think I need to think about it.
Okay.
Thank you.
I have a question. So, did you separate part of your samples to test your machine learning classification?
Oh, so this is actually our other students' work, but we of course separated some of the sources to verify whether or not these machine learning methods working.
Any more questions from the audience?
Why are there two clusters for repeating FRBs? What's the difference?
Yeah, two questions. Well, actually, this is very difficult to tell because this is just a two-dimensional visualization of about 10 parameters. So, but what I can say is there are weight of how much similarity each parameter contributes to each parameters. Then the most heaviest weight was on the width of the signal, how long signal had the duration. So maybe these two were maybe had a different time scale of duration. That's the maximum that I can say. Thank you.
Okay, let's thank Yuri again, and next speaker please.